So, can you see it and can you hear me?
Yes, perfectly, Jenny.
It's working good, thank you. Yes, I will talk a little bit about scenario tree models. Because as Khadin already mentioned, we had a number of case studies in STOC 3 that we used to test and develop the model. And the odd case, I guess, was the Swedish case where BVD has been eradicated. And the Swedish control program started in 1993. And that's the start of the y-axis in the graph that you see to the left. And there was good progress in the next 10 to 15 years. And we had the last case 10 years ago. And for a while now, we've had two main sampling routes, both based on antibody testing. And one is bulk milk testing with samples collected from the Swedish milk control program. And the other is testing of serum samples collected from beef cattle at slaughter. And the program is risk-based, so that herds with more live animal trade are sampled more frequently. And also to control the probability of introduction of BVD, there's a strategy to test animals purchased from member states where BVD is still present. So this risk-based sampling and the probability of introduction and the different sampling routes, these were things that we wanted to include in the assessment of disease freedom. And although these are input that can be included in the STOC 3 model, we soon found that the model will not give meaningful results if there are no positive test results in the data. And we only had negative test results from Sweden. So luckily, there's also already an existing method for this situation where disease is absent, and that's the scenario tree model. And this method was developed not so long ago, it was in this century, and it was presented and published 2007 by Martin, Cameron, and Gainer. But it's already well established. And I did a very quick search and found several publications. And these are just the scientific publications. But this method is often used not only in research, but in everyday work by epidemiologists like myself, who are involved in the planning and evaluation of surveillance. So the text here is very small. I try to highlight the diseases so that you could see the focus in these studies and the variation with these diseases with very different infectious agents, both bacteria and virus and parasites and prions. So why is the scenario tree model so popular and why is it called a scenario tree? So one reason is that you can quite easily capture the complex structure of surveillance systems, because usually surveillance is not just one simple random survey, but we have a combination of sampling routes, and some routes have a longer detection pathway than just to sample and run a test. So instead, we might have an animal walking around grazing, and we're not so interested in it, but then it dies and becomes fallen stock. And then it becomes very interesting for us to test. However, there's a certain probability first that the animal becomes fallen stock. And then there's a probability that this animal is not just sent for destruction, but is sent for necropsy. And once there's a new probability that the right samples are taken and it's submitted to a lab for diagnostic testing. And finally, if this animal is indeed infected, the test sensitivity is equal to the probability that the test result is positive. So all of these probabilities make up a chain of detection. And if you connect them, these all potential pathways where you can find an infected animal, you will get several branches in a tree structure. And I guess that's why it's called a scenario tree model. Here is a tree upside down. And all of these scenarios that happen in reality can be included in this type of model. What is also important and easy to include is that infections are not evenly distributed in animal populations, because the population in itself is very clustered with animals kept together in herds. And infectious diseases also tend to cluster. So this clustering could be a statistical problem, but with scenario tree modeling, it's easy to include these hierarchies in the model. And then I already touched on the risk differences, and perhaps one of the most unique features of this type of model is the easy way difference in risk is included. and is allowed to give additional value to test results from high-risk animals that we want to focus on in order to have a cost-effective surveillance. And the calculation of changes in confidence over time is typically Bayesian statistics, just as the stock-free model, where we have a starting point where we might have some previous knowledge or we don't, and we just have to assume nothing. But then we do some testing as part of our surveillance or control program. And based on that, we get an update with a posterior probability of freedom. And how well that probability stands over time, that will depend on the external infection pressure. And that is the expected incidence, or here, the probability of introduction of infection into this naive population. And if we look at the ingredients or the input needed for this model, this list in the blue box is what we would usually include in a scenario tree model. We would always need to include information about number of test results, of course. But there's also one thing that you don't have to specify in the stock-free model, but you must specify it in a scenario tree model, or it will not run. And that's the detection level, or what we usually call the design prevalence. And here's what that means. It's a fixed value for prevalence used for declaring the herd or the country free from the disease. So if we did a lot of testing, no case was detected, then how confident are we that the population is indeed free from the infection? For example, we may conclude that the probability that disease prevalence is below 0.2% or absent is 99%. And then the design prevalence is this 0.2%. And that's the detection level that this 99% probability of freedom relates to. And when you have hierarchies in the population and in your model, you also need to specify the design prevalence for each level. So typically we have the among herd design prevalence. That's the proportion of infected herds that you want to be able to detect. And the within herd design prevalence, which is the proportion of infected animals within a herd. Then we come to the output, the results. And when all herds in the population are test negative, then the estimated probability of freedom can be applied to all of these herds. And in the case then of BVD in Sweden, it looks like this. So first here, the surveillance sensitivity for each quarter of a year from 2012 to 19. And as you can see, it varies a bit, and that depends on how many samples and what herds were tested. And the solid line is the estimate for all cattle in total, and the dashed and dotted lines there are for dairy cattle and beef cattle separately. And the probability of freedom over time looks like this, and this is very high. Even if we started at a 50-50 probability of freedom, we soon reach close to 100%. And this is because the intensity of the testing is still high at the control program level, and it needs to be reduced to surveillance level. But I guess no one wanted to risk eradication and transfer into surveillance mode too early. So that was the scenario tree model. And for when to use this or the other method, I leave the word back to Khedi.
Thank you, Jenny. Yes, I can imagine that you now think